Hi, let's talk about MAMBA. It is overdue for us to talk about MAMBA and explain state space models. MAMBA has made a splash immediately after it came out, being called a potential replacement of the ubiquitous transformer. And it came to everyone's surprise that the MAMBA paper was rejected at iClear. In this AI coffee break, we will explain all the important things you need to understand about state space models, or short SSMs, and how MAMBA makes SSMs even better with selective state space models. MAMBA makes SSMs so good that they can compete with transformers, even though transformers have been the long-standing most popular architecture on all data types and all modalities, such as text, images, audio, video, genomics, and so on. Please use the chapters in the video to navigate to exactly the parts of SSMs and MAMBA that you're interested in. MAMBA was introduced by Albert Gu and Tri Dao, which you may know from Flash Attention 1 and 2. MAMBA's main contribution is to improve SSMs, which already were faster than transformers and used less memory than transformers, which is most important when modeling long sequences. But SSMs were not yet as performant as transformers, so all these acceleration bonuses and the memory we can save with SSMs came to the cost of accuracy. So MAMBA takes SSMs and improves them by making them selective SSMs, which are better or comparable to transformers judging by their quality of prediction. And SSMs are still fast at processing sequences, even long ones. But before we can understand the improvement of selective state space models, we first need to understand state space models. So strap yourself in for this ride. SSMs are usually part of larger neural network architectures because on their own they are not much. From a high-level perspective, they work like linear RNNs, where the output representation of the previous token and the embedding of the current input token are transformed and then combined. So yes, just like in RNNs, SSMs process one input token after the other. Now, to get into more depth, SSMs are also called as 4 models, which have 4 sets of matrices and parameters to process the input, namely delta, A, B, and C. All these matrices have different jobs. Delta modifies the weights in the A and B matrices. Then the modified A determines how much of the hidden state should propagate forward from token to token. The modified B determines how much of the input enters the hidden state, and C determines how the hidden state transforms into output. Now, in even more detail, SSMs follow 2 steps. First, delta does something to the matrices A and B during the so-called discretization step. Here, delta modifies A according to this specific formula, so now we get A bar instead of A. It also modifies B by following this other formula, and we get B bar, which we will use further down the line when processing input vectors. We will explain in a second why discretization is needed, but first let's gather the bigger picture about SSMs, and then we can understand this discretization step. For now, just assume that we need this discretization step in which delta modifies the entries of matrices A and B. Delta itself is a parameter which we could learn from data when training the SSM. Then with the A bar and B bar matrices, we go over to the linear RNN step. Like RNNs, SSMs work token by token to process a new hidden representation based on previous tokens at the current input token. SSMs compute a hidden state for each token, just like in the simplest RNN imaginable, a linear one. Namely, to get the hidden state for token T, we multiply the hidden state from the previous token, so T minus 1, with A bar, which is a linear transformation. Then we multiply B bar to the input embedding of the current token and add these two together. And this is how we get the hidden state for the token T in the sequence. But most of the time, we want to do something with that hidden representation at that time step. For example, we want to predict the next token or classify the whole sequence, whether it is ape DNA or not ape DNA, for example. To get a final representation for the current token, SSMs multiply C with the hidden representation of that token. Like in transformers, we can use this representation to do a softmax to classify, for example, which of the 50,000 words in the vocabulary is likely to come next, or any other task we can imagine. Great, so these were SSMs, and we will immediately tell you why SSMs are fast and great and can compete with transformers, but we promise to explain to you what's the thing with the discretization step and why it is needed and why we don't learn A and B directly and first need to modify A and B by weird formulae. Feel free to skip to the next chapter if this gets too technical for you, but we will try to break it down as much as possible, especially since this has something to do with the history of SSMs. SSMs come from continuous differential equations converted into matrix equation form. This means that continuous SSMs are differential equations that tell you how a variable h changes over time. For example, here, h changes like a sinusoid. H dot stands for the time derivative of h, which describes how h changes over time. So the equation here says nothing other than how h changes in the future depends on the current state of h plus an external factor. Does this not remind you of our linear RNN? There we basically had the future hidden state for our token given by the modified current state plus an additional factor, which happens to be the current input token. So our SSMs are just a discretized version of this continuous differential equation. And the theory says that in order to make this conversion from the continuous case to the discrete formulation with matrices, we need to choose a step size, delta, that tells us in how much detail to discretize. In the continuous case, we would move in infinitesimal steps along the curve. But in the discrete case, we take discrete steps from states to states. A larger step allows for larger jumps of h, but if we take them too large, we could fall off the curve and make errors in such a coarse approximation. Delta is a parameter that could be, for example, set to a scalar divided by the sequence length, because the sequence length kind of determines the number of transitions and steps that we need to do. But h has many dimensions because we initialize our input embedding with high dimensional vectors. So if we want to choose different step sizes for going into different dimensions, delta could be also a matrix which can vary in its entries. Theory we will not get into says that if we want to make the discretization step right, we must convert A and B from the continuous setting into A bar and B bar for the discrete setting with these formulae. Okay, we're done with this. Now let's get to explain why SSMs are so great. We all know that transformers are great, but nonetheless they have some annoying parts that scale quadratically, namely the self-attention sublayer, as it needs to compute scores between each token and every other token. So when the sequence length increases by a factor of 2, self-attention needs 4 times as much memory and time to compute. On the other hand, SSMs scale linearly. Adding one more token to the sequence means that we need to just do one more time the SSM computation. So when the sequence length doubles, the computation time and memory also just doubles, while for transformers it was quadrupling. Transformers became great language models, and historically they quickly replace RNNs because transformers are super fast. They can do their processing of each token in parallel without waiting for any results from the other tokens. But RNNs are slow because they need to wait for the result from the previous token to continue their computation with the next one. Now, SSMs are like RNNs and process tokens one after the other. Does this make them slow as well? No, because SSMs are like linear RNNs, meaning that they are fast and parallelizable at training. A training time where the whole input sequence is already seen because it's there in the training data, SSMs can combine and pre-compute and execute the linear transformations in parallel for all tokens. Only at inference time, where the inputs are produced one at a time, they need to process tokens one after the other. Okay, but how does this parallelization thing work during training, since we said earlier that we need to have the output of the first token to compute the next? Well, it all comes down to the fact that SSMs have linear computations in them. It is always the same matrices A bar and B bar and C that we multiply to our input token. Look, let's unroll what SSMs do and see how the representation looks like for the first token, where we assume that the hidden representation from the minus first step is 0. Y0 then looks like this. Then for the second token, it looks like this. Let's also write it for the third token so we can see a pattern here, but you can do yourself the math to check. And the pattern is this, and it's very regular. We have here lots of matrix multiplications one after the other, like C times T times A bar times B bar, irrespective of what the input will be. Only after this stack of matrix multiplication must we multiply with the input. So we can pre-compute all these matrix multiplications like this one or like this one. We can combine all these pre-computed matrix multiplications in one ginormous matrix, which we will call K. And we can also write the input vectors into another matrix. When we convolve K and X with one another, we get our outputs for all tokens at once, in one swoop. And convolutions are fast on GPUs, I assure you. So now to conclude the SSM explanation, SSMs are faster and not so memory intensive as transformers, which pays off for really long sequences. SSMs can continue processing even for long sequences where the transformer would need too long to finish or would throw a memory error, causing you to spend more money on GPUs with lots of VRAM. But SSMs do not give that sweet high task accuracy that transformers do, because SSMs are inflexible in the way they process inputs. They apply the same matrices delta, A, B, and C to all inputs without distinction between input tokens. But it would be better if SSMs could process input tokens differently, to esteem some higher than others, such that they can choose to remember or ignore certain inputs. Therefore, delta B and C should depend on the embedding of each individual token, which is the characteristic of selective SSMs. So selective SSMs use linear layers to compute different delta, B, and C for each input token. For example, for delta, a delta-specific linear layer takes in the current input embedding and computes a delta from it. And so does a B-specific linear layer, and the same holds for C. So now we get different delta, B, and C matrices at each input, and the SSM, now a selective SSM, can learn to focus on some tokens more than others. And this is a job that attention does in transformers. The only problem with these input-dependent delta, B, and C parameters is that we cannot use the convolution trick from earlier. Before, we could pre-compute all those matrix multiplications without needing to know what inputs will show up. But now we need to know the inputs already to be able to compute the matrices and their multiplications. Therefore, convolution becomes impossible. But the MAMBA authors present another trick to compute these things fast, called parallel associative scan. It relies on the algorithmic idea that even if something feels inherently sequential, we can store intermediate steps to do something quickly. Think of sums, for example. If we have the array 3, 1, 7, 0, 4, and so on, and we want to compute sums of its elements, it is better to compute the all prefix sums first, meaning that we add 3 to its predecessor, so 0, then we add 3 to 1 and get 4, we add 7 to 4 and get 11, and so on, because now if we want to compute the sum of just the last elements, we just need to do 22 minus 3. But more than these scan algorithms that compute things efficiently, one needs hardware-specific implementation that computes and stores things in the right type of GPU memory, because, see, in pure PyTorch, this scan is slower. So to make it fast, the authors read delta A, B, and C from slow HBM GPU RAM to fast GPU SRAM. They do the discretization of A and B in SRAM. Then they also perform parallel associative scanning in SRAM, multiply with C, and write the result back to HBM. I do not have the knowledge to get into details here, but I can point you to two great resources. If you want a pure PyTorch implementation of this, check out this awesome repo by Rudy Pei. And if you want a complete CUDA tutorial about associative scan, check out this tutorial from NVIDIA. The thing you need to know about MAMBA is that although in principle selective SSMs would be slower than SSMs because they cannot do the convolution, the authors could find a fast GPU implementation of an alternative way to compute things fast and in parallel, and MAMBA stays a linear time architecture. Okay, great, we now learned enough about SSMs and selective SSMs to finally understand the MAMBA layers. One MAMBA layer is composed of a selective state space module and of some other things as follows. First, a linear layer doubles the dimensionality of the input token embedding. A higher dimensionality gives the network more space to push around information, and some inseparable classes in the low dimension might become separable in the higher dimension. The authors use the 64-dimensional input embedding, so this layer increases dimensionality from 64 to 128. Then a canonical 1D convolution layer takes in the output of the previous layer. Its role is to push around information between the dimensions in the linearly upscaled 128-dimensional vector. It uses the swish, also named CLU, activation function. Then comes the selective state space module to process the output of the convolution like a linear RNN, as we discussed before. Then MAMBA does a gated multiplication, namely, we take the input, push it through another linear layer, then throw it into a swish or CLU activation function, and the result of this is multiplied to the output of the selective SSM. The author's intuition behind this operation is that the multiplication is a measure of similarity between the output of the SSM, which contains information from the previous tokens, and the embedding of the current token. Then a linear layer reduces the dimensionality back from 128 to 64, and this was it. To get MAMBA, we just need to stack multiple MAMBA layers a few times on top of each other, and unlike other SSM architectures, they do not need some other layers in between because they can just use the same layer all the time, in the same way in which transformers are composed of just transformer layers on top of one another. And if you think that this architecture is complicated, then think about how the transformer layer also has a lot of components. Self-attention, a feed-forward network, normalization, residual layers, and so on. But the whole innovation in MAMBA paid off. MAMBA is as performant as transformers. Just look at these scaling laws. The perplexity of MAMBA and that of transformers decrease both in the same way when doing language modeling on the pile dataset, and MAMBA is even better as the sequence length increases. For perplexity, lower is better. MAMBA also outperforms all other SSMs or attention-free models. And all this by being super fast. At a 128 batch size, MAMBA of 1.4 billion parameters can process 1,814 tokens per second, while the transformer has long given up by throwing an out-of-memory error. At a batch size of 8, MAMBA can process 744 tokens per second, while the transformer processes just 265. And this is no wonder, since flash attention 2 in transformers needs way more time with increasing sequence length than the incredibly optimized MAMBA scan. At 256,000 long sequences, where a naive scan implementation in PyTorch goes out of memory, MAMBA scan needs 10 milliseconds, while flash attention 2 needs about 1,000 milliseconds. Yes, the y-axis uses logarithmic scale. The authors also tested MAMBA on downstream tasks, and we see great accuracies across the board. You know, the bolder the numbers, the better. And it's better than transformers or attention-free methods. But what we also wanted to show is the great data type diversity that MAMBA can cover. MAMBA works great for DNA sequence classification tasks, where the model classifies the species given a DNA sequence. Here, sequence length increases a lot to even 1 million tokens, and MAMBA performs better than competition. On autoregressive audio modeling, MAMBA outperforms the previous state-of-the-art, which was an SSM. In sum, MAMBA works great for many data types and challenges the transformer, which so far was the architecture that worked great on all these data types. Of course, time will tell whether SSMs will come and replace transformers, as the community will do even more experiments with MAMBA, also going to even higher parameter numbers than the authors did. Funny enough, peer review first rejected MAMBA in its first round at iClear, but it's not like anybody in machine learning has time to wait for peer review approval to build on top of MAMBA. So far, we already have a mixture of experts MAMBA, a vision MAMBA to process images. There is also MAMBA Byte that uses MAMBA to learn directly from raw bytes, not relying on tedious tokenizers. Of course, having bytes as inputs makes the sequences very, very long, and where that was a problem for transformers which scale quadratically with sequence length, it is no problem for the linearly scaling MAMBA. Is this the comeback of RNNs in the form of SSMs? My subjective opinion is that RNNs were powerful but slow all along. All that was missing was enough research attention to make them fast as well. But everyone was busy researching linear attention and flash attention instead. The RWKV paper, Reinventing RNNs for the Transformer Era, did first attempts to make RNNs catch up with transformers that everybody was working on to improve, but now MAMBA finally nailed it. Wow, thanks for making it until the end of this video, where we have a little surprise for you. If you like this video, do not forget to like and subscribe, but also check this out. We released AICoffeeBreak merch. We wanted to make something nice and something that goes a little bit beyond just the channel logo. We wanted cool designs for you to wear, so check out our store and see whether you like something there. By buying something, you get some cool products while giving a few dollars to support a cup of coffee to refill Miss Coffee Bean's caffeine supply. We hope you find something that you like, but most of all, we would love to see you here for our next video.